All right, so one of the main applications for integrals is to be able to calculate the area of a region in the plane. Now, this is going to build off of the application of Riemann sums that we kind of covered in like chapter 1, chapter 2, a little bit, here and there. So before we get into the actual, details, let's first review how we use sigma notation. So if you recall sigma notation from maybe algebra or maybe your pre-calc class, it's used to write the sum of a set of terms in a very compact way. So if you want to write the sum of n terms, a1, a2, a3, all the way to an, we can use the sigma symbol, which is basically the capital letter S in Greek. And then we use our index starting with I equals 1 to n, and we write a sub I over here, if you recall. And this basically is telling us that we're going to evaluate, or that we're going to add up the 1 through n terms where each term is equal to ai. So this would be like a1 plus a2 plus a3, all the way till you get to n. N could be 10 or 100. It could be whatever. It has to be a whole. It just has to be a whole number. Now again, you don't have to start at 1. You can start at 0. You can start at 10. It just depends. But usually, when we're using this to add up areas, we're gonna usually start at 0 or 1. That's pretty common. But again, technically, you don't have to start at 1. Now let's go over a couple of examples when we have sigma notation for different forms and how we can apply some of the formulas and properties. So if we're adding, the sum of the first 6 terms, so I equals 1 through 6, and each term is equal to I, this means that we're going to be adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, which will then give us 21. So this is equal to 21. And 2, we're adding the terms from I equals 0 to 5, where each term is equal to I plus 1. So starting at 0, that means we're going to have 0 plus 1 be our first term. And then our next term will be 1 plus 1. Third term will be 2 plus 1. Then 3 plus 1. Then 4 plus 1. Plus 5 plus 1. So again, you're adding 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so we get 21 again. In 3, we're adding the terms from I equals 1 to n, where each term is equal to f of x sub I times delta x. And this is basically not giving us a explicit value for each term, but what this means is that we're going to have f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, all the way until we get to f of x n times delta x. So we're not going to have an explicit value because we're not given the actual function. But this is going to be key in this chapter and really in this course, because this is the kind of type of notation that we're going to be interpreting a lot of the concepts through. Okay, so a couple of properties when we have a summation notation is that we can multiply the terms in your series by a constant or scalar k. So if you have the sum of k times a sub I, you can actually like essentially think of factoring out the k, and this will be the same as k times the sum of a sub I from 1 to n. So you can basically factor the k out. The second property says that we can add two series up. So we have terms ai and bi in two series. Then we can actually break it up as the sum of the a sub I terms plus or minus the sum of the b sub I terms going from I equals 1 to n. And now we have, let's look at a couple of formulas that we can break down. So a couple of formulas that will be very useful will be if you have the sum of the terms where each term is equal to c from I equals 1 to n, this will just be equal to c times n, where c is a constant. So it's not a variable, it's a constant. So if it was maybe like, if c was like 10, this would just be equal to 10 times n. Second formula is if you have the sum of the I terms, where, from 1 to n, so each term is equal to I, this will be equal to n times n plus 1 all over 2. Let me box these guys, actually. They're a big deal. Third one, if you have the sum of the terms where each term is equal to I squared from I equals 1 to n, this will be equal to n times n plus 1 times 2n plus 1 all over 6. And the fourth formula says that if each of your terms are equal to I cubed and you're adding from I equals 1 to the n term, then this will be equal to n squared times n plus 1 squared all over 4. So let's see how we can apply these. Okay, so problem 4, we're going to evaluate this sum for n equals 10, 100, 1,000, and 10,000. So each of the terms are equal to I plus 1 over n squared. Now, you don't want to, go through a tedious process of, adding 10 terms, where you're plugging 1 in for I or 1 in for n, and then adding it to when you plug in 2, plug in 3, plug in 4, and then all the way to 10 for here. Then here you add 100 terms, 1,000, then 10,000. It would take you forever. Well, not forever. It would take you a very, very, very long time. You wouldn't be able to get through calculus. So what we want to do is find some clever way to break these into combinations of these formulas, where it's simply going to be you just plugging in a number for n and evaluating it quickly. So in general, let's rewrite this as 1 over n squared times the sum of the I plus 1 terms from I equals 1 to n. So you can factor out that 1 over n squared, because this is the same as like I plus 1 times 1 over n. So this factors out. Then within here, we can use one of the properties to break this into two sums. So 1 over n squared times one of the sums will just have the I term. The other one will be plus the sum where each term is equal to 1 from, I equals 1 to n. Now from here, we can rewrite this as this, because we got the formula right up there. So we can write this as 1 over n squared times n plus 1 over 2 plus, and this one, this is a constant. Your constant c is just 1. Here is just c is 1. So this will just be 1 times n. So this will just be n. And that makes sense because you're just adding 1 to itself n times. And then we just do some algebra to simplify this, distributing that. We can break this up as n times n plus 1 over 2n squared plus n over n squared. You can factor out the n from there. You can then have n plus 1 over 2n. Here you can factor out n as well, plus 1 over n. And if you want, you can combine them, or you can just leave them like this, but I'm just going to combine them. So I can multiply this by 2 over 2. So then this will be n plus 1 plus 2. So on top, I'm going to have n plus 3 all over 2n. Now from here, I have a simple formula where I can simply plug in n equals 10, n equals 100, n equals 1,000, n equals 10,000 for this. So then if I want to evaluate this for n equals 10, I'm simply going to get 10 plus 3. So I'm going to get 13 over 2 times 10 over 20. So 13 over 20, I'll get 0.65 for that. If I plug in n equals 100, 100 plus 3, so I get 103 over 2 times 100 over 200. That will simplify to 0.515. Plug in n is 1,000. I get 1,000 plus 3, so I get 1,003 over 2,000. And this would simplify, or this would be equal to 0.50150. And for n equals 10,000, I'll get 10,000 and 3 over 20,000. Which would be equal to 0.50015.